Thank you, madam. Okay. Can I share the screen, madam? Is it visible, madam? Yeah. Good evening to all. Thank you, madam, for giving this opportunity. Now, today we discuss about the quantum algorithms for AI. Especially, we focus on Grover's and Shor's algorithms in this context we discuss. But before going, already I saw previous material also showed in this program WhatsApp group. Dr. Jayaprakash sir, he is telling about quantum principles very efficiently. But before going to my Showers and Groves algorithm, before this, for my purpose, I am going what is ontology, what is supervision, what is going to next level measurement, quantum measurements. Just I give the brief introduction, one point. Now I let us slowly go to the quantum algorithms. Before going in my own style, I'm telling what is before going this quantum algorithms in these two algorithms. First, what is classic and what is quantum? Classical computers and quantum computers, like a sandwich and burrito. Sandwich is your classical computers. Quantum computers is commander burrito. For example, if you go to classical computer, works with bits which are like choosing between two fixed options, like your sandwich. Whereas goes to the quantum computing, now what we are going, quantum computers use qubits, quantum bits we are using, which can be both at a time once. This is the big sometimes we were into dish. In this we have various ingredients, everything we are adding. And whenever you go to this, why we use today classical computing. So in this works with bits and zeros and ones, but you go to light, switch on, switch off. In earlier, we are going like classical computing, either yes or no, two options only. All programs, images, AI models, data processing using combination of these only zeros and ones, bits. So now go to just simple ice cream grill. In this ice cream skill, what happened in the superposition in earlier classical computer means you are going with classical bits is using either only one flavor, either vanilla or chocolate ice cream. This is your option. So I choose any one. But now when you go to qubits, quantum bits in superpositions like spilled vanilla or chocolate ice cream means I can combine both combining is possible. That's what we are told, zeros and ones and both also possible. And next one is entanglement. What is entanglement? It's like a pair of synchronized pairs. Whatever, for example, you go to French fries. In this, you and your friend is each order a plate of fries at different restaurants. If the fries were entangled, then what happened? The moment you dip your fry in ketchup, your friend also fry automatically gets dipped. So distance does not matter. It's a what you call without our action. So whatever your friend is some other without unconscious, automatically we are doing this is does not matter. The fries remain synchronized. So similarity in quantum entanglement, two qubits stay mysteriously connected. A change in one instantly reflected in another, no matter of the distance. This is entanglement. One more topic, what I need in this entire our program is measure quantum measurement. Okay, this is the way of the path. Next, quantum computing. So in this already I told now only repeatedly zeros and ones both at a time we are using. You have so many possibilities if you go both. So when you are going to quantum parallelism, what is this? For example, if you go to buffet and single dish, if I go to any hotel and I order one single dish, that is one option. Another one is I want buffet. At a time, I have multiple dishes. I can choose anything. I can eat anything in that selected dishes. So this is one buffet. In this buffet, what happen? Regular computer is like ordering one dish at a time. But when you go to quantum computing, it's like a buffet. You can order everything, so pizza, burger, and sandwich, or all whatever the menu in the food, all the food menus are available. Of course, these all are AI related. That's with maximum showing a pizza and burger only. And goes to quantum measurement. This is also last one in the prerequisite what I required. Mystery box cake. So for example, if you are having a cake inside a mystery box is unable to open. I can't see, this is not transparent box. In this, before opening it, it could be a chocolate or vanilla or strawberry, I don't know, but the moment when you open the box, instantly you find out what is the flavor it is. So this is mysterious box. This is called quantum measurements. This is non-technically I'm talking what exactly I need. So what is existing aren't just faster computers. They think differently like a chef who can prepare thousands of recipes at once instead of cooking them one by one. Recently, I saw in one YouTube video also, he's showing that video. At a time, he can prepare 10 dishes in the house, 10 dishes at a time he is preparing. So like that, one chef at a time in the same 1 hour time he can prepare multiple dishes is possible. Just you see. So he at a time he can multiple dishes he are preparing. This is nowadays. This is mainly focused on the computing. Now again I go to next topic, quantum computing with AI. So nowadays, AI today, like deep learning, natural language processing, robotics, requires a huge amounts of computation. Computation is required. So huge amount. In earlier, what we have simple 2 into 3, 6. 20 into 35. These all are small amount of calculations. But nowadays, by using this, huge amount calculations are needed. That is computation. So training large models like already we are know ChatGPT, we know recognition systems image, and searching in massive data sets. Massive data sets we are using in research also. Optimizing million parameters, handling uncertainty in decision making. So faster training models. What are the advantages when you are going quantum computing over AI? First one is faster training AI models. So training today's deep neural networks takes days or weeks, even supercomputers you have. But you go to quantum algorithms like quantum linear algebra solvers could solve certain matrix operations exponentially very faster. So this could make a training much quicker and cheaper. So fast training with quantum with AI models. Next one is better search and optimization. That is what we are discussing about the Shor and Grover algorithms. So AI often needs to search through huge spaces possibilities. Example, finding the best path in self-driving cars and tuning models hypothesis matters. So classical search is a old fashion, that is a very slow linear or exponential search. But when you go to the quantum, in quantum, Grover's algorithm is important algorithm. It is a quadratic speed up. Unstructured search. AI can find the solutions faster. In detail, I talk about the unstructured structure next level. Quantum optimization algorithms could help solve logistics, scheduling, or protein folding problems in record time. Next point of advantage with quantum AI is handling uncertainty and probabilistic reasoning. AI systems deal with the probabilities. So multiple predictions, data sets, in that they are taking the multiple options, in that only automatically, in that direction only they are finding the solutions. Quantum systems are naturally probabilistic, so they can represent to compute these models more naturally. so that could lead more human-like reasoning in artificial intelligence. Another one is enhanced data processing for big data machine learning. So here AI works enormous data sets. Simple data nowadays data set is slowly go to big data set also. Quantum computers can store process certain high dimensional data more efficiently using quantum futures. So this power quantum machine learning QML, which uses quantum states to represent data in the classical pattern. One more advantage with quantum AI is new AI capabilities beyond the classical computers, just like a quantum physics revealed the phenomena of classical physics could not explain. Quantum AI might allow new forms of learning, creativity, and problem solving nowadays. And real world examples quantum plus AI, Google Quantum AI, IBM Quantum, drug discovery, finance, in logistics, airlines also we are using. So, what is the big picture for quantum AI? Classical AI is already powerful but limited for computing speed, energy cost. So, in classical AI, we have a limitations, but when you go to the quantum AI prompt, in this, it is a faster training. How much is this faster? We see in the algorithms. Better optimization, more natural handling and probability, access to solutions classical AI can't reach. So that's why quantum computing for AI is significant. It could unlock the next generation of intelligent systems that are faster and smarter. So simply see this diagram. In this classical AI, this is limitations, slow training. In classical AI, I'm talking slow training and huge data set we are accessing. And next, sorry, huge data set you are accessing. And next, go to optimization bottlenecks. Whenever go to quantum computing, key features are already we discussed now: superposition, entanglement, and parallelism. But if you go for plus quantum computing with AI, then it is faster in training and better optimization, probabilistic reasoning, new capabilities. These all are possible. In quantum computing, we are simply talking about Shor's and Gross algorithm. Not only this, we have huge algorithms. First one is Shor's algorithm, Gross algorithm, HHL algorithm, and quantum PCA, quantum support vector missions, quantum neural networks, quantum bottleneck missions, quantum approximate optimization algorithm, quantum reinforcement learning. These all are the algorithms we have in the quantum AI. But basically, we are going with these two algorithms. Just tell what is the purpose of each and every algorithm. Just go through this, and later we go for in detail our algorithms. First algorithm is Shor's algorithm. It is what is the main purpose of this algorithm? It factors the large numbers efficiently break the RSA encryption. So in this, what is relevancy? It is not directly used for training models, but critical in AI security. If RSA is broken, all AI systems could AI services encrypted data sets. So what is the impact is shows why quantum resistant AI systems are necessary showing. Whereas goes to the Grover algorithm, in general linear search, if you go for order of n is the possibilities for searching. Here we are using order of square root n is enough. For example, you are using four options for searching. Square root of 4 is 2. Two options is enough. Comparatively 4 and 2 very less amount only. If you go to lakhs of amount of n value, then square root of n is very less amount. That we can see with an example. In this hyperparameters tuning, searching through millions of possible settings for neural networks, future selections, finding the best subset of future in large data sets. So in database search, quick loops in large training data sets. What is the use? Mainly quadratic speed up makes A more efficient in optimization, heavy risks. So once you go to another algorithm, HHL, main purpose is solve AX equal to B exponentially faster than the classical methods it is using for training regression models. And go to the quantum PCA. This is extract principles component of data sets. It is relevance to AI relevance is dimensionally reduction for large scale of artificial intelligence, and also pattern recognition in images and speech and genomes. And go to the quantum support vector missions. This is mainly used for quantum kernels for classic classification. It is also fast used for faster and more powerful classification of high dimensional data sets like text and images. Next, quantum neural networks. It is used for quantum circuits structured like neural networks. In this ARLS is hybrid quantum classical deep learning and also for can discover patterns classical network might. Next, bottle quantum missions. In these quantum versions for energy-based probabilistic models, it is mainly used for generative AI, images synthesis and text generation, and also for modeling complex distributions. Quantum appreciative optimization, it is used solves the combinational optimization problems. It is using training AI models with many discrete parameters and also resource allocation for artificial intelligence system. And last one is quantum reinforcement learning. It is used for enhancements to trial and error learning, robotics, games, adaptive agents, and also for handling huge state action spaces more effectively. So mainly, if you go to the all the algorithms and showers and growers and remaining other algorithms, I go with only two algorithms. Mine original purpose is factoring integers for Shor's algorithm, but AI, security, and cryptography. What is the benefit for artificial intelligence? It drives post-quantum secure AI. And go to the Gross algorithm, unstructured search, hyperparameter tuning, future selection, dataset search, quadratic speed up. So like this, everyone solve linear system for HHL remaining also like this only already whatever we discussed that is I put in a table. Now mainly we go for the quantum algorithms. First algorithm I'm going with Shor's algorithm. In this session, we are going to discuss about the Shor's and Gross algorithm as they are very significant and frequently used ones. Before dealing in detail of these algorithms, let us consider some analogy where we can actually use this in simple examples. Go to this example. In this example, the core of Shor's algorithm is solving the problem. So given a large number, already starting I told about the RSA concept. What is RSA? RSA already you know. RSA for security, asymmetric key algorithm. In this, what we are taking P and Q, two prime numbers, we are taking calculated the n value, n equal to P into Q, Z equal to P minus 1 into Q minus 1, and your calculated relative prime number for D. And next, go to the calculate the E value, E into D equal to 1 Z mod. So then once you got this, then you calculate the encryption value of your plain text is goes to the P power E mod N. After decryption, C power D mod N, that is the decryption. This is we are doing. But here the RSA algorithm is okay, but the condition is the RSA algorithm, whatever the prime number, for example, I am taking P value is 3, Q value is 11. In our regular class also we are talking about P value 3, you take it, and Q value 11 and take the value N equal to 33, Z equal to 20, like this. For understanding purpose we are telling, but the condition for RSA algorithm is you choose any two prime numbers P and Q above 1024 bits. So once you are taking more than 1002 bits means just imaginary what is the number. So that's why RSA algorithm we can't break. But here my question is give a large number I told in the Shor's algorithm. When I go to the Shor's algorithm, I am giving two prime factors. So 20, for example, you take above 1024 bits. Before going to this, I go with a small example, not that much big numbers. Modern encryption methods for RSA depends on how hard it is break down to large numbers. So for RSA, before going, I just go with a small example. For example, I am taking a 323. What is the factors for 323? For example, it is very easy. Simply you are telling 17 into 19 is okay. But in case if you go to according to RSA algorithm, in RSA algorithm, I told already more than 1024 bits. Here in this example, I am asking more than 2048 bits. You take it. For this, what is your number? Like this, your number. Now simply 35, 32, like this I am not taken. That is minimum 2048 bits means just imagine. Still I given dots only. Why? Because this much big number you need to select for RSA prime numbers in the RSA algorithm. So in RSA algorithm, if you choose two prime numbers, in the two prime numbers, one is like this, another one also same like prime numbers means we can't break the RSA. So that would take a classical computer thousands of years to find out the factor. So I told you need two factors. How you take the factors for this number, that's what make RSA is high secure, so it is not possible for 2048 bits. But when you go for the quantum, what happen, already we know quantum is, we are simply going, classical computer is either 0 or 1 only, but when you go to quantum computer with AI means you go to 0, 1 and one more is both, that is called superposition. So whenever you go to, also qubits can interact in special way called entanglement. So without, even though it is a for, it is go to entanglement where changing one qubit can affect the another, even if they are far apart. See this, how this is happen. In this what happen? We are using a spinning coin. Until you look at it, it's both head and tail. So while coin is spinning, we can't judge which is the, either it is showing finally head or tail. While coin is moving, what is the situation? So think spinning coin, until you look at it, it's both heads and tails. It's very difficult. So why is quantum computing is that much powerful is, this is the reason. What is the possibilities we have? Superposition we know, we have entanglement is there. Quantum computers can explore many possibilities at once. This is the only reason quantum computing is more powerful. In classic computers tries each number one by one only, but quantum is millions of numbers simultaneously we can handle. So in simple terms, if you go in step by step, Peter Shor discovered a way to use a quantum computer to factor big numbers fast. But already we told in earlier, before this RSA algorithm is a big number, it is very difficult to find out the non-trivial factors. But when you go to Shor algorithm, it is easily can find like that Peter Shor told. So here take a big idea, very simplified step by step. Break your number with Shor's algorithm. Let us pretend we want a factor 15. I don't know 15 factors. Assume this is a big number. So what you do, you take a factor 15 and sorry, some here power off. Is it visible, madam? Hello? Is it audible, madam? Yeah, thank you. Sorry, power off here, that's why I disconnected. No. Okay. full here. Now power off. Okay, I will open. No problem. Okay, once power off time, I will open. Okay. Okay, sorry. Yeah. Okay. So in shower algorithm, step by step is first one is you choose any number, prime number. In this prime number, let's assume I am taking small number. Actually, I need to take a big number which is more than 2048 bits. But practically for explaining it's very difficult. I am choosing a small number and you feel it. I don't know the factors. Now, what is the goal is find two numbers that multiply to 15. So already we know 3 into 15. 3 into 5 is the 15. But imagine you don't know the factors. So here I am using the Shor's algorithm works on quantum computer. Step 1, pick a random number. But condition is whenever you take a random number, that is always your existing number. What is the number? 15. For 15 only you are talking, less than 15 only you need to choose. So I start with pick a number A, less than 15 is, let us example, I take A value is 2. We will use this number to find a hidden pattern. What is the hidden pattern? Step 2, use quantum computer to find the period. What is period? Now the quantum computer does something magical. It finds period on this section f of x equal to a power x mod n, where a value is 2, n value is 15. So you need to calculate the f of x equal to a power x mod n. What is x? See here. So f of for x is starting with 1, 2, 3, 4, 5, 6, so on up to n only you can go. So first one is f of 1. What is f of 1 here? This is first one is f of x equal to a power x mod n. F of x is x I am taking as a 1. First one is I am taking as a 1. So that's the reason. Once you go here, what is the values here? F of 1. F of 1 is equal to 2 power x, 2 power 1 mod 15. So what is this meaning? 15 is divisible, 2 power 1 is 2 and zeros and 0. This is the remainder is 2. So that's the value is 2 and goes to the f of 2. What is f of 2? F of 2 means what is the value of f of 2? 2 power x. A is already 2, x is 2 mod n is 15. So 15, 2 power 2 is 4, 0, 0, this is 4. So that's the value is 4. Next go to the a power x. X value I am taking 3. So 2 power 3 mod n. So 15, 2 power 3 is 8, 0, 0, 8 is the remainder. If I go to 2 power 4, x value is I go to the 4. Then what happened? 2 power 4. 2 power 4 is 16. So 15, 16, divisible is 1, 15 and remainder is 1. So next, what is the next value? Going like this, so on. This is the 4 is 1. Next go to the f of 5. F of 5 means you are going with 15, 2 power 5. What is 2 power 5? 32, I think so. So 32. 32 means 15 2s are 30 and remainder 2. Just observe the 2. What is this 2? Already we have first attempt to 2. So here in f of 1, whatever you taken, that remainder is 2, next remainder is 4, next remainder is 8, next remainder is 1. If you go after this, again coming 2 means for f of 6, again coming 4. If you want, you can cross check. 32 2s are 64. So f of 6 means what is the value? 64. And go to the 15 is 15 4s are 64. Just see. So what happened here? First, you are taking one example here. In this example, f of x is equal to a power x mod n means f of 1, f of 2, up to so on going, up to what time we are going? A continuous cycle. If it is completed, up to that you can leave. So f of 1 is remainder 2, f of 2 remainder 4, 3 is remainder 8, 4 is remainder 1. That's all. If you go to f of 5, no use. Again come the same remainder 2, again 4, again come 8, again come 1. This is called, whatever the pattern you have, this is called step by step. Every step, four steps is there. So after every four steps, you are getting the same values. This is called cycle. The repeating cycle, this cycle is called period. So that already I told here. Use quantum computer to find the period. So how I find of the computer find the period? F of x equal to a power x mod n. N is actually you need the factors for n only. N is the 15. For that n 15 you want means f of x equal to a power x mod n. A is you take any number. Okay, you are telling why sir you're taking 2. Why can't you take 3 means 3 also you can take it. But any number you can take it, and that condition that number is reasonably less than n and required, because here I am taking a small number. For example, I take 14 sir. 14 is n is less than 14 is less than n means it is true. But for understanding purpose, we are taking a very less number. When you are going real-time application, it is 2048. More than bits means it's imaginary. Then you can take any number. Easily you can get the answers. So this is called period. Once quantum computers can find the period instantly using their ability to explore many values at once. So use the period to find the factors. Here the trick is, if the period is OR, so what is the period now? In this, you are telling cycle is up to 1, 2, 3, 4. Again come the cycle. This 4 is called a period. So what is the period now? R value is the period. So find the factors. If the period is R, what is the R value now? 4. And it's even. Now it is a even or odd number. This is even. Then you follow the rule is, you just calculate greatest common divisor a power r by 2. A power r by 2 plus or minus n. For this you calculate the GCD. Now what is the R value? For this example, R value is 4. So what is the A value you are choosing? A value is 2, you are choosing. Power, this is 4 by 2. This is plus or minus n. N is already we know 15. So what is this 2 power 4 by 2? 2 power 2 plus or minus 15. So 2 power 2 is 4 plus or minus plus or minus 1 comma 15. So plus or minus 1, 4 plus or minus 1 comma 15. So 4 plus or minus 1 comma 15 means what is the value? 4 plus 1 is 1. 4 minus 1 is 1. Both with 15. We need to calculate the GCD. Now it is, we need to calculate the GCD. So now what is the actual answer for this? You need to calculate GCD for this example. A power r by 2 is a power 4, 2 power 4 by 2 is 2 power 2 is 4. 4 plus 1 is 3 comma 15. One more GCD you need to calculate is 3 plus 1. A power r by 2 is 2 power 2 4. 4 plus 1. 4 plus 1 is 5 comma 15. You calculate the GCD for these two. So here you see. So what is this? For a is equal to 2, r is equal to 4. You need to calculate 2 power 4 by 2. 2 power 4 by 2 is 2 power 2. 2 power 2 value is 4. Then GCD for 4 plus 1 and 4 minus 1. 3, 5, 10 and 5, 15. Already you know how to calculate the GCD. For this calculation 3 into 15, actually in algorithms also, you know, in general also you can calculate, or you can go the programming. If you go GCD program, if you insert in this quantum computing also, we know 3 and 15 means just go to 15 minus 3, 12, 12 minus 3, go to, what is 12 minus 3? 9. 9 minus 3 is goes to 6. 6 minus 3 goes to 3. So finally 3 is the factor. So like that in programming you can do, that is different aspect. So GCD 315. You just calculate the 315 GCD is 3. 515 again, this is 515 calculation is the 5. Now what is the result is GCD of this and GCD of this. These two are is nothing but your multiple factors. So 3 into 5 is the 15. So what are the steps you followed? First step is you choose any value which is less than n, and find the period. Period is means nothing but your one cycle. Now compute the GCD. GCD for what? 2 power r by 2 plus or minus 1. So GCD for 2 power, sorry, a power r by 2 plus or minus 1, comma, n. Then only you are getting two concepts, GCD for 4 plus 1 and GCD for 4 minus 1. So then you are getting 3 and 5. This is the final output is 3 into 15. See how simple we get. Same you assume for the large number. Large number, for example, 2048 bits you have. You choose a any value, and a power we are doing again the same scenario we are following. Then you are getting whatever you are getting, that period means simple. I don't want total calculations, just I want to go with the remainder. Once you are repeated means ignore, don't go for multiple times. One is repeated, 2 4 8 1 again come 2 means automatically it comes to 4 8 like this only. So one cycle completed means period you will get. Even though you take n number of digits also, periods is not like n numbers. For example, I am taking 10 digits number. For this 10 digits numbers also, one certain period is completed. Maybe period is 2, period is 4, period is 6. Like this single numbers only will come, not like a huge number of digits. Don't think 2048 bits means we get 1024 bits size of period. No, period is always we are getting very less number. We are focusing on periods only. So why this break RSA algorithm? So this is the shower algorithm already you know. So in this you are compute the GCD for plus or minus, and finally you get the factors. In one direction GCD 3, and the direction you are getting 5. The finally factors are 3 into 5. You are getting 3 into 5 is 15. So why this breaks RSA algorithm? Why? Because actually RSA algorithm is having 20 bits for more than 1024 bits long prime numbers we are taken. But even though RSA encrypt the huge numbers like 2048 bits long, they are made by multiplying two joint prime numbers, just like any two prime numbers, 3 into 5 like this. But with hundreds of digits. But here, for example, I am taking simple single digits. Classical computers would take thousands of years for factors them. Classical computer means for this you need to calculate the factors means of 2048 bit is not a small size. For this, how you calculate, it's very difficult. That's why we are going to classical computers is taking thousands of years to find the factors. But quantum computers using Shor's algorithm can factor them in hour or even minutes also you can break. Why? Because you are taking your numbers. In that numbers, you are applying Shower algorithm, calculate the period. Once period means easily plus or minus with your n, you can calculate the GCD value. So it is taking very less hours or even minutes also, sometimes it is possible. So this big is a big deal. Why? Because all online banking, email, credit card information, private messages use RSA encryption nowadays. Now, in case quantum is full-fledgedly introduced, full-fledgedly implemented means all whatever asymmetric key algorithms using in these applications, everything is we can break. Then what about the RSA encryption security issue? When quantum computers become powerful enough, they can break these encryption. That's why the government and tech companies are working on post-quantum cryptography. Again, we need security on the quantum. So new encryption systems that even quantum computers can't break this. So what is the difference classical and quantum? Already you know all these things. Only in this I need to know about I need to talk about the time to break RSA algorithm. In time to take RSA algorithm is take thousands of years for classical. That's why nowadays still running RSA security asymmetric algorithms. Whenever go to quantum, so it is within hours we can break the RSA algorithm. So in Shor's algorithm is not possible to apply in the classical approach, but it is run efficiently in the quantum concepts. So go to the next algorithm is Grover's algorithm. Again in detail I will explain the Shor's algorithm. In Grover's algorithm, if you are going means in this we are using unsorted library. Imagine you walk into a huge library, 10 lakhs, more than 10 lakh books, 1 million books is there, all randomly placed in shelves. Why? Because in library, students taking and shitting, they are not put in the proper place in different place. They are putting all randomly placed on shelves. You can now exact title, you can find the exact title of the book you want, but there is no catalog or sorting system. This is a huge books. So that's a classical in research. If you are focusing means in classical research, what happen, you check one book at a time. You check. Once you are going to this, classical binary search works only if the books are sorted in alphabetically. In classical search, what happen? You want to check one book at a time. Worst case is 10 lakh books you need to search. Otherwise, you won't get your book. Already I told it is not in the order. Proper order I am not put in the alphabetical or in the engineering separate, medical separate like that. Because of this, if you want to go for finding your special book, whatever you required, minimum whatever the searches. Worst case means you need to search each and every book. If your book is the last book, then 10 lakh checks to find the right one. So could take say days or weeks for doing this. But same if you are going for classical binary search, works only if the books are sorted alphabet. So in linear search and binary search, linear search at least we can find out in 10 lakh checks, whereas goes to binary search is not possible. It is in the alphabetical order or numbers means ascending descending order, then only we can do. So works only if the books are sorted alphabetically. But in our case, the library is unsorted, so binary search also not possible. It is not at all possible. But go to the Grover's algorithm. Whenever go to Grover quantum search algorithm, a quantum computer can do something special. It looks at all 10 lakh books simultaneously in superposition. Already we told in superposition, entanglement, and quantum measurements, what we discuss at a time to multiple tasks. So if it tags the correct book without knowing where it is at. So it amplifies the chance of finding the book. In case if you go to 10 lakh books, how many searches you need is root of 10 lakh. What is the root of 10 lakh? 1000 square. 1000 square is the actually, that's why I'm taking 10 lakh books for our example, easily forget the answer. 1000 square. What is the 1000 square? Is nothing but 10 lakh. So if I get 10 lakh book, even though it is not in the sequential order in alphabet, simply at a time doing multiple tasks, square root of 10 lakh, square root of 10 lakh is 1000. Within 1000 steps, you will find the correct book almost for sure. So that's what happened now. In earlier past case, we are telling 10 lakh. Now you are completed 1000 searches. So how far your speed? 1000 times your speed comparatively your classical search. So what are the steps you are following in the Grover's algorithm? Consider all books at once. In quantum mechanics, let us the system create a superposition as it is if it is examining every book simultaneously. So at a time you can do, already I told one in starting, I told one chef can do at a time multiple dishes. So same way as a human we can do in quantum, it is examining every book simultaneously. So mark the right book. A special, for example, as a special oracle identifies the target book internally but does not reveal it yet. So simple steps is boost the probability. What is the probability? The algorithm increases the likelihood for the correct book being chosen. Pick the book. When you finally measure, you almost certainly pick the book you were searching for it. So easily we can get. So in this Grover's algorithm, you provide a quadratic speed up. Quadratic speed, already I told if you have n means root n. Classical search is n steps. Worst case, I told I am talking current step one. Worst case only. If you have unsorted books, 10 lakh means 10 lakh searches. Root of 10 lakhs is the quantum search. That much difference is there. This is instant magic, but for huge data sets, it can save years of computation time. So Grover's algorithm fosters search in unsorted library. If sorted library, classical search, binary search also you can take it, but quantum is more powerful. But there is condition is either sorted or unsorted. You can go in the Grover's algorithm. In general, you need to go with the sorted elements only. So in this, what happened? Problem: find a specific book in a large unsorted library. So what happened? You go to the linear search, choose one book at a time and go to the 1 lakh books and check is 1 lakh. It is classical. Whereas go to Grover's quantum search, what happened? Just use the imply the Grover's algorithm at a time, multiple possibilities are searching with that book. So what happened? Whatever the searches you are using, that is go to the root of the worst case searches. Worst case searches is 10 lakh. Root of the 10 lakh is comes to maximum 1000 checks. So whenever this is about the concepts. Now go to the algorithm. If you algorithm in this, pick a random number. So in Shor's algorithm, what you are doing? Pick a random number. Already I taken 2 and less than your number 15. Now you calculate the GCD for A and N greater than 1. You are already found a factor. So what happened? This is the GCD of the 2 and 15. 2 and 15 GCD. What is the, so if it is greater than 1, you have already find a factor, but it is no have the GCD, because for 2 and 15 GCD is 1 only. Why? Because common factor is 1 only. It is equal to 1, but we are asking greater than 1. Greater than 1 is not there for your number. That's why in earlier I am taking simply n is equal to 15. Why can't you take any a value instead of 2, 15? Why can't you take the 3? 3 also I can take it at the time my example. If I take a is equal to 3 and n is already 15 and rule is less than n, that is satisfied. So next step is a power. You need to calculate the period, or this is all are okay. But I can't go to algorithm. I'm just tell them generally. Now go to algorithm. In algorithm, what is the first step? You calculate the GCD of A and N. A and N already we have the GCD. If you go to 3 and 15, we have the GCD is 3. So once you got the already find a factor, if GCD is greater than 1 means other than 1 it have a factor, then you already have one factor. Otherwise, quantum order finding. Prepare a uniform superposition of all possible exponents. Perform modular experiment for a power x mod n. Already x you know, x is 1, 2, so on up to less than n. Apply the quantum finding transport QFT to extract the hidden periodicity. Now measurement. What is measurement? Get function C by Q is delta equal to K by R, where R is the period. Use the continued factor to reduce the R value. Why? Because simply you are telling one, for example, if I tell 6 periods, so for example, I got the remainder is 2, 1, 4, 3, now 2K. For example, I got like this. You can stop here. Again, you are telling here 1, now I stop means what is the period? 6, which is wrong. So classical post processing. What is this? If R is a odd number, already in earlier what we have for our example period is 4. 4 is the even number. So simply I am talking about the even number. Even number means what you are doing? A power R by 2 plus or minus 1 comma n. For this you calculate the GCD. That is even number in our example. Now we need to discuss about the odd also. If R is a odd number, so period is not required, is mandatory for getting even number. Maybe period is 5 also possible, period is 7 also possible, any number is also possible. So R is an odd number. R by 2, is it possible? No. R by 2 when possible? If period is even number, then only R by 2 is possible. So R by 2 is not possible. is equal to minus 1 mod 1 repeat a new a. So then you are searching for a new a, and otherwise compute. So simply you are taking instead of, and for example 14, I told first example, why sir you are taking a value 2, why you taking a value is 2, why can't I take as a value is 4, 15, n is equal to 15 already is there, your condition is less than n, you are taking a value simply take 2, why can't you take 3, already I given the example, because if you take 3, first step itself satisfied and close, that's why I taken 2. Why can't I take 14? 14 also less than n only na, n is 15 only na, why can't you take? The reason is, if I take like this, what happen? We can't get the period. So 15, for example, 15 is there. You are taking 14 is the a value, a power x. What is the a power x? 1. 14 power 1. What is the remainder? 15, 14 remainder is 14. 0. Sorry, remainder is 0. This is 14 is the remainder. Next, what is the next one? 14 power 2. That is 28. So again 15 and 28 remainder. What is the remainder? 15 ones are 15. 13 is the remainder. So slowly what happened? It is reducing. So okay. Up to what reducing? Up to 13, 12, like this it is coming. Then it is come under minimum 14 iterations, then maybe we are getting a odd number. So once you are getting an odd number, maybe possible. Sometimes we are getting even number also. If you are getting a odd number, it is not possible. Then you go to minus 1 mod n, repeat until we satisfy and calculate a new a value. Simply a value 2, I try and I am not getting, a is equal to 3, I am not getting, a is equal to 8, randomly I take and not getting, a is equal to 12, I am taken randomly, I am not getting. Like this you are doing, finally you find out the any one a, best a. In my example, luckily I taken a is equal to, it is a best way. So here GC. So you can take any number, 14 also take, 13 also take, 12 also take, but you need to satisfy this rule, then only you can go next level. If it is not satisfied, then you find out repeatedly the a value. Otherwise, once you are taking any a value, you are getting a by a even number as a period, then a power r by 2 is, you can calculate because of even r value. Then you do simply plus or minus 1, 2 factors. This is a non-trivial factors of n. So the runtime for this is order of log n cube. So this is threatens RSA encryption. Because of using, we can break the RSA encryption. So here simple, I am going in detail. This is a high level Shor's algorithm. So, but we discussed it in our example is low level Shor's algorithm. Give a composite number n and find its prime factors. So reduce factoring to period finding using quantum Fourier transform QFT. So choose a random integer a. One is in between a is in between 1 to n. Calculate the GCD for an. If GCD an is not possible, then you go to the continue. If sim GCD an is possible, you are getting that decide this is a factor. And quantum period finding subroutine. If it is not equal, first register the steps. Register x, m qubits, even enough the repeat exponents with qubits. So next what happen? Create a superposition of exponents. For this, the formula is 1 by square root of q sigma x equal 0 to q minus 1, not q minus 1. Now go to the x and 0. What is this meaning of x and 0? This is called ket notation. Once you write like this is called ket notation for so and so element. This comes from what is this called? This is comes from ket notation. This meaning is called simply mod. We know this is mod x, but like this we are writing in this quantum means this is called ket notation. This comes from direct notation is a quantum mechanics. In quantum, if you have an idea quantum mechanics means, then you know the this symbol. This is called ket notation. a two register quantum states. Here we are going quantum register states. Two are registered in this. First one is describe the action of quantum operations, unary operation and binary operation. Simply go to the modular explanation controlled cooperation. In this controlled operation, you apply the unary operation and go to the optional measure register. This is collapse y sum yields to value of this. This is the equation. These all are the equations in algorithms in detail we are using. Finally, we are getting some outcome with A with C value, which is a high probability measurements. Classical report, when I go to the post processing of the classical report, just verify A power I is identically equal to 1 with mod n. So for example, I go to the A power R value. A power R already in our example 2 power 2. 2 power 2 is identically equal to 1 mod n or not. So 15 with 4. This is the remainder. I need the remainder. Remainder is 1 or not. No, it is not a remainder is 1. 0, 0, 4, which is not wrong. Pick a new A and repeat this. So anyhow, same whatever I told in this algorithm, same we are telling in different style. So it is a classical high level we are talking. In low level means very step by step, point to point we are tracing each and every element. That is low level algorithm. In this also finally we are achieving a power r by 2 minus 1 plus or minus 1 with n. But this is only possible when you got the period value is even number. If you are not getting even number, until get the even number, you repeat and change the a value. This is about the Shor's algorithm. What is the final result? I need the factors, non-trivial factors of n. Next, go to the Grove's algorithm. So in Grove's algorithm, main motto is search a unstructured database. Already we saw how you are doing. In this, what are the steps you are doing? Get notation for yes. You are talking 1 by root n sigma get notation x. Apply the Oracle OIF files the phase of the correct suitable states. So apply the diffusion operators. These all are the searching algorithms we are using. Main goal of this is also we have high level and low level algorithms. In detail, we are going in the low level algorithm. Find a marked element in unstructured database size, which book you want. And already we talk about the Oracle library. We have unsorted structure, so many books. In that specific author book, specific book I need means you need to tell what book you need. So find a marked element in an unstructured database size. Just use the amplitude application via Oracle and diffusion operator. So you need to find out the problem with function f of x where 0 to n minus 1 x value. 0 to n minus 1. F of x is 1 if x is a solution. So whenever you got a solution, it is true. Otherwise, is false. Need to find some x where f of x equal to 1. Until f of x equal to 1, you need to finalize, search for the x value. You can change the x value. So here starts with n equal to log n base 2 qubits in get notation 0. So apply Hartman gates to all qubits, uniform superposition for all states. So whatever the states you have, just way, because in binary search what you are doing in general, if it is a sorted elements means by two like this, finally easily you can search the element. Whenever go to the quantum Gauss algorithm, quantum AI Gauss algorithm, in this first you need to go with uniform superposition of all the states. For example, you have 1000 means 1000 books. You need to go with the uniformly, you need to search at a time. Simply you go to one set of access. In that set of access you are searching means it is not possible. A quantum black box that most solutions for flipping their solutions for keynote cat x minus 1 power f of x with the cat x. So x is a solution, phase flips, sign changes. So these all are easily, you can't understand the quotation. If you know the quantum mechanics, you can understand what is cat x and what is rotation and what is Oracle F, everything. And go to the diffusion operator. This is mainly these operations are we are using for inversion about the mean value finally to calculating. Once you are using, what is the use is increasing the amplitude of the marked states and decrease the amplitude of the unmarked states. So once you go to the unsorted library, in that unsorted library 10 lakhs books is there. Whenever you want to go to the search, already I told root n. How you got the root n? You just increase the amplitude marked states and decrease the amplitude unmarked states. So whatever you are searching, that is go to the another set of state. Whatever unmapped, that all are go to the another state. So in thousand books at a time they are taking, in the thousand books they are mapping and separate it even though it unsorted. So in this iteration, apply the Oracle F, apply the diffusion D, and repeat the same performance or equal to pi by 4 root n by m iterations. N is the total number of states, how many states you have. M is the number of solutions. For example, I want to find out one book in the library means we have 10 lakh options is there. So 10 lakh options is the n value. What are the number of solutions you have? That, for example, at a time you can search in the library. For example, I'm not talking about the sorting concept. 10 lakh means 10 lakh not a dump. They are in the properly in the library. In the library properly means separate rows, one row. So you are going at a time, I'm choosing four rows, four members at a time searching for the same book means what happened. Worst case, okay, 1,000 rotations required, but maybe best case means anyone catch the book before at a time. I'm talking about the at a time. So row one person, row two, one person, row three, one person, like that you assume at a time. So 10 members at a time, 10 rows searching means one row maximum books is nothing but you are searching. For example, I am using 1,000 members at a time. 1,000 members, 1,000 books searching means worst case 1,000. Otherwise, maybe 100 or 90, anything is possible. So that is we repeat the whatever the perform your value for this the states n total states and number of solutions for getting iterations, multiple iterations you can find out, and finally you calculate for this how many iterations you required is pi by 4 root n by m iterations. What is the measurement for this? The measurement is measurement the quantum state. You measure the quantum state, which highly probability you get the marked solution, let it be x. So finally solution you will get, the problem is root n, order of root n queries instead of order of n. Already 10 lakh means worst case 10 lakh, root of 10 lakh is your order for this result. This is about the Grover's algorithm. What are the real-time applications you have in the Shower's algorithm? So efficiently factoring large numbers, already we know, breaks the classical cryptography. That's why we go the cryptography security also nowadays. Their tech companies are going. Applications in AI. What are the AI applications in this Shor's algorithm? AI models and data sets are often protected with RSA or ECC encryption. Shower algorithms can break these, forcing AI systems to adopt post-quantum cryptography. So that's why we are focusing nowadays post-quantum cryptography concept. For example, you go secure cloud-based AI services, medical AI or financial AI need quantum safe encryption. So next, federated learning security. If in federated AI, data is encrypted before being shared to across the devices. But Shor's algorithm shows the risk of using RSA ECC for this, motivating now quantum resistant secure aggregation. So quantum secure aggregation. And go to the applications beyond the AI, cyber security and cryptography, break RSA, ECC, Diffie-Hellman protocols, you know, the backbone of internet security, impact of banking, e-commerce, secure emails, blockchain and cryptography. If you go to blockchain and cryptography, Bitcoin is there, and electronic cure, ECC is there, and sufficiently powerful quantum computers running shores could break wallets of signatures. So national security, whatever the national security, military communications, classified government data, and intelligence release, RSA, ECC. So shores algorithm pushes a government to adopt post-quantum cryptography standards. So drug discovery, the drug discovery, molecular simulations. So factoring isn't directly useful here, but Shor's algorithm proves quantum computers can outperform classical systems, which fuels investment into quantum algorithms for chemistry. So same in Growers also, what are the applications you have? Quant Quadratic speedup in searching unsorted data. In applications of AI means hyperparameter optimization, Turing neural networks hypothesis like learning rate, number of layers, dropout rates, search incentives, and go to the depth and intensity. In this, Grovers reduce the search spaces from nn to n by square root of n. Future selection is A often needs to choose the best subset of futures from large data sets. Grover helps the search the possible subsets of more efficiently. So database search in machine learning, go to the machine learning concepts, faster search through massive data sets, search images, documents, and go to the model checking verification. In model checking verification, AI safety requires the checking a large state spaces for flows. Govers can accelerate this verification process. Grover algorithm easily can do the verification. Go to the beyond the AI. Already with these all are AI applications. Beyond the AI, again go to the same cyber security, password cracking, optimization problems, searching engine and information retrievals, cryptanalysis beyond the Showers algorithm. Grovers can speed up the attacks on symmetric encryption. So symmetric encryption means this algorithm, AES algorithm, SHA algorithm, Bullowfish algorithm is there. So in cryptanalysis beyond the Shor's algorithm mainly focus on the asymmetric, and this Groves algorithm in A is symmetric algorithm we can do. In this example is A is 256 security effective drops, A is 128. Already you know in advanced encryption algorithm and this algorithm okay 16 rounds. But in A's algorithm we have 128 bits, 192 bits and 256 bits. Here we have 10 rounds, 12 rounds and 14 rounds. So for this also quantum attacker can do. This is the about the beyond the applications of AI. So shower algorithm reshapes the security landscape, forcing AI and every digital systems to adopt the quantum safe cryptography. Whereas goes to Growl algorithm, it provides the practical computational speed up, especially for search and optimization, making it useful in AI, finance, logistic, and cybersecurity. This is the about the Shower's algorithm. This is about the Grover's algorithm. So this is simply about our Shower's and Grover's algorithm. Any doubts? Hello? Yeah. Please. Okay. Thank you, madam. Yes, madam. Okay, welcome, madam. Thank you for giving this opportunity also. Thank you, madam.